Welcome to today's central exercise session. We'll be discussing sheet number 1 today. As usual, you're welcome to ask any questions you might have. We have a chat channel dedicated to that. The chat is available on the platform chat.twam.de. And you can join us on this channel here, MA9714-CE for your questions. The chat will be moderated. Today's moderator is Eileen Carlson. Hi, Eileen.
Hey. Do you want me to say something about myself?
Yes, please.
So some of you hopefully recognize me from Math 1, where I was also helping out, but I'm a tutor slash moderator in this course. Like normally my job is being a PhD student at TUM. So I like math.
Okay, thanks a lot. So as usual, I'll stop after every problem or sub-problem, see if there are any questions. So if there's anything that comes to your mind, just post a message to this chat channel and we'll try to answer your question. Okay, let's start right away with problem sheet number 1. There's 3 problems for today's central exercise session, and I hope we managed to at least briefly discuss all of those. Problem number 1, C11, is about differential equations, specifically of the differential equation 2f of x. 2f of x plus f prime of x equals 0. And we do have an initial value 2, and that initial value is f of 1 equals 1. So we're looking for a solution to this differential equation that also satisfies this initial value condition here. And we've talked in the videos about how to solve differential equations of that type here. What we do is we first solve this equation for f prime. So we get f prime of x equals minus 2f of x. So basically we're looking for a function such that the derivative is minus 2 times the original function. So basically differentiating reproduces the function up to a constant. And I hope you all know which function we can use to solve this. So the solution to a differential equation of that type is always of the form e to something times x. And well, if you differentiate a term like e to this power of something times x, it's something due to the chain rule is put in front of the derivative. So that shows up as a constant here. So that's what we need to put here. We need e to the power of minus 2x. And if we differentiate that, we get exactly minus 2 times e to the power of minus 2x, which is minus 2 times f of x. So that satisfies the differential equation. And of course, we can multiply this differential equation here, by any constant, and it still stays valid. So what that means is we can multiply this solution by any constant. Any gamma in R will still give a valid solution. And if we differentiate that, the constant just stays the same. So we get minus 2 gamma instead of just minus 2. And this gamma is no part of the function. So this is still true. And that's all the solutions we can get, also called the general solution of this differential equation. Basically, the set of possible solutions. General solution of the differential equation, that is then f of x equals gamma times e to the power of minus 2x, and gamma a real constant. And now that we have this general solution, the initial value comes in. Basically, the idea here is to single out one of those solutions here that also has this specific property. So what we do is we determine the constant gamma that satisfies this property here. And hopefully such a constant exists. So now we use the initial value. F of 1 equals 1. So for our solution, f of 1 equals gamma times e to the power of minus 2 times 1. And that is supposed to be equal to 1. So we can just solve that for gamma. And what we get is gamma equals e to the power of 2. So the solution to our differential equation with this given initial value is then f of x equals e to the power of 2 times e to the power of minus 2x. And that solves question 1.1. So let's see if you have any questions about that.
So far, no questions. There's someone typing, so I can take a general one in the meantime. So someone asked when the solutions to the exercise sheets will be uploaded.
I'll usually upload those after the tutorial class for the exercise sheet, so on Thursday sometime.
Do you want me to wait for the ones typing, or should I?
I guess we can just continue with 1.2
Yeah.
and then get, I mean, we're getting back to differential equations in 1.3 anyway.
Yeah.
So we can also take these questions
so
there. Okay, let's go on, not lose any time on. So let's go on with C12. That one is about eigenvalues and eigenvectors. So we've learned that to solve systems of differential equations, we somehow need to simplify the matrix that is involved. And we'll talk more about that in C13 later. The idea is basically to find a basis such that the matrix transformed to that basis looks as simple as it can. And the simplest we can reasonably expect would be a diagonal matrix, if that is possible. And eigenvalues and eigenvectors are basically the way to find out whether that is possible and to compute such transformations as a basis if it exists. So that's what we do in C12. Let's start with A. So we have this matrix capital A here, -2, -6, -6, -3, -5, -6, and 3, 6, 7. And we are given eigenvalues of that matrix already, so we don't need to compute those. The problem statement says eigenvalues are 1 and -2. And the question is, can we find a basis such that the matrix transformed to that basis is diagonal? So in other words, can we diagonalize that matrix? We know the eigenvalues already, so what we have to do is compute the corresponding eigenvectors and then see if those eigenvectors span a basis of R3 in that case, because the matrix is a 3 by 3 matrix. Okay, so we need a basis of the R3. To compute the eigenvectors, basically what we do is we solve the defining equation for eigenvalues and eigenvectors. Remember, a vector is called an eigenvector if a v, where v is that vector, is the same as lambda v. Lambda is the eigenvalue. V is the eigenvector if such vectors and values exist. Eigenvectors are never 0. Keep that in mind, because if v is 0, obviously the equation is always true for any lambda. So that's trivial. So the interesting vectors are not going to be the 0 vectors. An eigenvector by definition can never be 0. An eigenvalue can. So an eigenvalue of 0 is perfectly fine. So basically we know the values for lambda, 1 and -2. We just use those, and when we solve for v. And solving for v is basically equivalent to solving A minus the identity matrix, sorry, lambda times the identity matrix, times v is 0. And that means what we are looking for is the kernel of this matrix A minus lambda I3. So we determine the kernel of A minus lambda I3. And that kernel is the space of all eigenvectors to that eigenvalue. And of course, the kernel also includes the zero vector. Otherwise, it wouldn't be a vector space. And this is called the eigenspace of the eigenvector lambda. So we're going to compute these eigenspaces. And we're going to start with the eigenvalue 1. So the eigenspace of A for the eigenvalue 1 is the kernel of A minus 1 times I3. Or the kernel, let's see, we have A. So A, that was minus 2, minus 6, minus 6. So if we subtract 1 on the diagonal, we get minus 3, minus 6, minus 6. Then we get minus 3, minus 6, minus 6. And finally 3, 6, and 6. You can already see the rows of this matrix look pretty similar. In fact, the two rows here are just 2 times the first row. So in other words, we can simply subtract 2 times row 1 here and 2 times row 1 here, and we get 0 rows. So this kernel is the same as minus 3, minus 3, 3, and then 2 0 rows. So what do we have here? Well, this here, this is our pivot element. These 2 columns correspond to free variables. And that means we get a 2-dimensional eigenspace. So let's try to write that down. So this is spanned by, let's start with setting the third variable, so x3 to 1 and x2 to 0. And then x1 can just be determined through this row here. So that says is basically x1 is the same as minus x2 plus x3, right? So what we get here is a 1 for x1 if you substitute 0 for x2 and 1 for x3. So this vector here obviously solves this equation. And then we need a second one that is linearly independent. To do that, we just set the second free variable to 1 and all the others to 0. So like this here. And then the first coordinate simply becomes a minus 1. Again, according to this equation here. So this is the solution space that we get. And more precisely, this here is a basis of the solution space. Right, so that here, those 2 vectors, that is a basis of the eigenspace for the eigenvector 1. So we get 2 linearly independent eigenvectors for this eigenvalue 1. Same thing for the eigenspace for the eigenvalue minus 2. So we determine the kernel of A minus minus 2 identity matrix. Please note that this effectively means the kernel of a plus 2 times identity matrix. And well, if we do this computation, we get the kernel of now a plus 2's on the diagonal. That would yield 0, minus 6, minus 6, minus 3, minus 3, minus 6, and 3, 6, 9 here. And again, we can transform that matrix easily. So, for example, what we can do is well, let's first let's first swap those two rows here to get a pivot element in first row, first column. So we have -6, -3, 6 in the first row. We have 0, -3, 3 in the second row. And the third one is the same, -6, -6, 9. Then we subtract the new first row from the third row. No operation is necessary here because we have that 0 already. So we get kernel -6, -3, 6, 0, -3, 3. And here we get a 0, -6 plus 3 is -3. And here we get 9 minus 6, that is a +3. And you can see if we now simply subtract the second row from the third one, we get the desired form. So the first row doesn't change, the second row doesn't change, and the last one becomes a 0 row. So this time the matrix has rank 2. We have this and this pivot element here. We have one free variable corresponding to the last column, x3. And that means this eigenspace is spanned by, well, let's set the free variable to 1. Then the second row here gives us the equation x2 equals x3. So x2 needs to be the same as x3. That's also 1 then. And this first row here gives us the equation, let's see, x1 equals x3 minus 1 over 2x2. So we get 1 minus 1/2, so that's 1 over 2. So this vector solves all of the equations. That vector is in the kernel then. And of course, as we only interested in the span here, we can scale that vector by any factor other than 0. So for example, we can multiply that by 2. And that also gives us a solution. So that's also an eigenvector. Okay, so this vector is now a basis of the eigenspace of A for the eigenvector -2. And if you now look at all three vectors, so the eigenvectors that we get, those were 1, 0, 1, -1, 1, 0. And now we have 1, 2, 2. And those three vectors are now linearly independent. So this is actually a basis of R3. So we have found a vector, we have found a basis of R3 that consists of eigenvectors of A. And that means if we transform A to that new basis, then we should get a diagonal matrix. So instead of the transformation matrix, we call it basis B. And then we have a transformation matrix that transforms from B to the canonical basis C. That transformation matrix is given by just these eigenvectors here as their columns. So it looks like this. And then we can transform by just using the inverse of that matrix times A times that matrix. So we're transforming that to the matrix representation of that linear mapping with respect to the new basis B. And if you do the computations, that should not be too hard. What you get is this matrix here. And you can see, hopefully, that these first two columns, those were eigenvectors for the eigenvalue 1, and indeed the eigenvalues 1 also appear here. And this last column, that was an eigenvector for the eigenvalue 2, and that appears in the last column here. So that order always corresponds, right? The order of the eigenvectors in that transformation will correspond to the order of the eigenvalues here in the diagonalized matrix. And of course, if you choose another order, then you'll get a different diagonal matrix, but still the result is of course fine. Okay, so that is the transformed version of that matrix. So in that case, the matrix A can be diagonalized. So let's see what questions you have on that topic.
So I'm still waiting for people to type for this one. So I'll do the questions for the first one while we're waiting. Okay. So two people wondered about the variation of constant. So when do you need to consider variation of constant, and when can you just have gamma be in R?
Scroll back a little. Should have left some space here. I will next time. So just a second, let me rearrange that. Okay, variation of constant. So the idea of variation of constant is to be able to solve inhomogeneous differential equations. So that means if you have a differential equation that looked like this, for example, so that was our original differential equation. And now let's add some inhomogeneity, any term that doesn't involve f directly, right? So like this one here, just add x or x squared or sinus of x or whatever you want. That's an inhomogeneous term here. And if you have a differential equation like that, then you can use, hopefully, variation of constant to solve that. What you do here is you first solve the homogeneous variation. So you pretend there is no inhomogeneity first. You do just what I've done before. You obtain f of x equals gamma e to the minus 2x as the general solution. And then you pretend that you know the solution to the inhomogeneous differential equation by just varying this approach a little. And instead of the constant, instead of this gamma here, you just use a function that is yet to be determined. So instead, you make the ansatz f is c of x, c is any constant, or any variation of constant, any function depending on x, times e to the minus 2x. So you replace this gamma here by c of x, and that's why it's called variation of constant. Yeah, instead of the constant, you just use a function, so not a constant anymore. And then just substitute that into the original differential equation. So we substitute that into f prime of x equals minus 2f of x plus x. And once you do that, you will get a term where the c's vanish, but the c prime will stay. And what you can then do is solve this for c prime of x and then integrate. Integrate to obtain c. And that in turn gives you a solution for the inhomogeneous problem. So once you have that c, you can just use that here in place of the constant. So this, with the c that you obtain, is then a solution to this inhomogeneous problem. And the general solution of the inhomogeneous problem can be obtained by taking this particular solution and adding all homogeneous solutions. Same thing as for systems of linear equations. Yeah, you want to solve an inhomogeneous system of linear equations, you compute one solution and you add the solution space of the homogeneous system. Basically, the same idea works here. There should be examples of that in the homework section, I think.
For example, H1.5.
For example.
Yeah, there are examples.
Good.
Okay, so now I have questions for 1.2.
Good, let's have a look at those.
Do they have to compute this T inverse AT, or to get the diagonal matrix?
Well, in that special case, I do already know what the outcome has to be. So I don't have to bother computing that actually. Yeah, I know that the matrix A can be diagonalized. And if I know the order of eigenvectors here in my transformation, I know the order of eigenvalues on the diagonal. So I know the outcome. I don't have to compute anything anymore.
You can, of course, double check if you did it correctly by doing it, but
it doesn't hurt, but in turn, it does also cost some time. So your decision.
Okay, and then there's a question about the eigenvectors. What if the corresponding eigenspaces are linearly dependent, or the vectors you get from this? What would you do about the t's?
So as we'll find out this week, the eigenvectors for different eigenvalues are always going to be linearly independent. So that's good. So the only thing we need to make sure is that we find enough linearly independent eigenvectors for each eigenvalue. And of course, it might happen that this doesn't work. There are matrices that cannot be diagonalized, and that's just because they have eigenvalues, but not enough eigenvectors for one of those. That happens, and in that case, well, the methods that we learn will not be applicable. There still are methods that you can apply, but yeah, that tends to get technical quickly, so we're not going to discuss that.
And then someone wanted a recollection of how you get the span from the eigenspace.
We'll get the span from the eigenspace. So
is it possible to get a repetition of how to get the span from eigenspace? Was the question.
Let's start with this one. This is probably easier here. So here I have Rao echelon form for my matrix. So what we've learned is how to solve a system of linear equations in echelon form. Basically, what you do is you look at the pivot elements, which are the elements basically on the staircase that are non-zero. So in that case, this here is an echelon pivot element, and this is a pivot element. And here is a 0, so there's no pivot element in row 3 and column 3. What that means is the columns without pivot element, those correspond to the free variables. So any value you set this variable to yields a possible solution. And that's exactly what we are doing here, basically. So if we take this here, then we could say, well, x3 is a free variable. Then we go up one row, this here, solve this for x2. We've done this here. So x2 equals x3. And for x1, we use this first row, solve it for x1, which we've also done already. So x1, basically, x1 is x3 minus 1 over 2 x2. x2 is equal to x3, so we can just take that, substitute it in here, and then we get 1 over 2 x3. So the set of solutions of this system of linear equations is then x3, that's free. x2 is the same as x3. And then we get 1 over 2 x3, where x3 is in R. Or in other words, if we take out the x3, then that's all multiples of this vector here. So the span of this vector. Basically, the way I computed that is I substituted 1 for this x3 here, because I'm taking all multiples of that anyway, so I can choose any value I want that is not 0, and then multiply by any factor I want. Yeah, so I'm taking 1 here, and then I solve for x2, and I solve for x1, and I just put in the corresponding values here. And maybe let's go back to this other one here. So this was the echelon form for the first matrix. Only one pivot element, no pivot element here, none here. So 2 free variables. And I did the same thing. I started with x3 as free variable, set that to 1 and all the other free variables to 0. And then I computed x1. Yeah, and it turns out that has to be x1 here. I did the same for x2, set x2 to 1, set all the others to 0, and compute the corresponding x1. That needs to be -1. And that way, I always get linearly independent vectors in my solution, because if you look at that block here of free variables, that makes sure my setting of ones and zeros makes sure that this always gets me linearly independent vectors. So that will always be a basis of my solution space. Right? And I'll just compute the x1 from that. I hope that helps.
So next question, since it's still on the page. So in the case of eigen space of -2, could we also use the Kreuzprodukt with the first two rows when trying to determine the span if the third row is 0?
I didn't quite get that one.
I'm not sure what Kreuzprodukt is, so.
Outer product, I guess.
Yeah.
Cross
Okay.
product. Did he say of what he wanted to take the cross product?
With the first two rows when trying to determine the span if the third row is 0.
Why would that work? I couldn't really figure out why that should work, actually. Maybe it does, but I can't think of a good reason. So in general, no, don't do that. Also, even if that works, it would only apply to 3x3 matrices with that very specific configuration of 1 0 row, and that's something that doesn't happen too often.
Next question: must A be a square matrix?
Yes, we always be talking about square matrices here. Yes.
And then to reiterate, I mean, we have answered it before, but how do we know that we can diagonalize a matrix, or when we can do it?
So we can do it if and only if we can find a basis of the space that we're looking at, basically the R to the number of columns of the matrix. We need to find a basis of that that consists of eigenvectors of the matrix. Then and only then can the matrix be diagonalized. And we learn about conditions for when this works in the videos this week.
Okay, then maybe we cap it, and I'll come with extra questions if they come, like if there's more.
All right, so let's have a quick look at part B. Try to keep that a little shorter. So here we have a matrix B. It looks like this. We have 1, 2, -1, -1, 0, -1, and 0, -2, 2. And again, we are given eigenvalues of that matrix. And those are 0, 1, and 2. And now, again, to determine the eigenspaces, what we have to do is we determine the corresponding kernels. So for the eigenspace of eigenvalue 0, correspond the kernel, we determine the kernel of B minus 0i3. So that's the kernel of B exactly. 1, 2, -1. Yeah. -1, 0, -1, and 0, -2, 2. And to compute that kernel, well, what we do is, for example, we subtract 2 times row 1 here. We add row 1 here. And we get, let's see, 1, -1, 0. Here's a 0 plus 2 -2. And here we get 0, -2 plus 2. So as you can see, just adding the second row to the third one will yield a 0 row. And we need to find a solution for that. Again, here's 2 pivot elements. No pivot element in the last column. So we can set x3 as our free variable. We set x3 to 1. And then we compute corresponding values of x2 and x1 that make that work. For x2, we look at that row here. And we see that says x2 is equal to x3. So we also set a 1 here. And that first row says x1 is equal to x2. So again, a 1. So that is our first eigenspace. And you can see an eigenvalue of 0 is perfectly acceptable. Then we need to compute the eigenspace for the eigenvalue 1. So that's the kernel of B minus I3, or the kernel of 0, 2, minus 1, minus 1, minus 1, minus 1, and 0, minus 2, 1. And in this case, we need to make sure that we have a pivot element here in that position first. So we need to swap rows. Let's put the first row on top because it has a 1 in that position. So we get minus 1, minus 1, 1, 2, minus 1, minus 2, and 0, minus 1, 0. Then we can add 2 times the first row to the second one to simplify that. So that yields a second row of, let's see, 0, minus 3, and 0. Yeah, and obviously subtracting a third of row 2 from row 3 will give us a 0 row once again. So we get minus 1, minus 1, 1, 0, minus 3, 0, and 3 zeros. Again, we have 2 pivot elements here and here, and we have a free variable for the third column. So again, let's set that x3 to 1 and compute the other values. On the second row here, that gives us the equation x2 is 0. So that doesn't depend on x3. And the first row gives us the equation x1 is minus x2 plus x3. So that's 1. So this is our second eigenspace. And the last one works in the same way. Now the eigenvalue is 2. So we need to compute B minus 2i3. And then the kernel of that. So that would be, let's see, minus 1, 2, minus 1, minus 1, minus 2, minus 1, 0, minus 2, 0. Okay, so we add 2 times row 1 to the second, and we subtract row 1 from the third. And that yields, let's see, copy the first row. Here we get a 0, a minus 4, and a minus 2. And here we get a 0 row right away. So basically, again, the same situation, 2 pivot elements here and here, and a free variable corresponding to the third column. So again, we set x3 to 1. We use this row here to solve for x2. And this here says x2 is minus 2 over 4, so minus 1 over 2 x3. And then x1 is minus x2. So with x3 being 1, we get minus 1 over 2 for x2. And we get 1 over 2 for x1. And to make things look a little neater, we can just multiply this vector by 2, scale it up, and we get 2, minus 1, and plus 1. So that's our third vector. And again, we have a basis of R3 that consists of eigenvectors of B. And that basis is 1, 1, 1, 1, 0, 1, and 1, minus 1, 2. So again, if we set the transformation matrix, call it S this time, with these 3 columns here. So again, that is the transformation from our basis B, let's call this basis here B, to the canonical basis C. Then we get S to the minus 1 times B times S is the desired diagonal form. And that is 0, 1, and 2 on the diagonals. Right, because again, that corresponds here to the order of eigenvectors. So that's the 0 here. That corresponds to the orange eigenvector. We have the green eigenvector. That was an eigenvector for the eigenvalue 1. And finally, we have this pink eigenvector here that corresponds to the eigenvalue 2. So just make sure the order is the same, and then you don't need to actually compute anything here. Okay, so again, this matrix can be diagonalized, and here's the eigenvector basis. And actually, when you're done with this week's videos, you should even be able to say that this matrix can be diagonalized without any computation at all. But we'll talk more about that next week. So, questions?
There we go. So do you always have to write kernel when you do these computations? Because in the lecture, kernel was not written.
Depends. So the formalism here would require that technically. If I'm writing the eigenspace is equal to, then I need to write the kernel here. Of course, I could also just have a look at that matrix and transform that without it being equal. I would just write arrows then, yeah, or implications. And then at the end, I could write this eigenspace is equal to that span. That would also work.
Do they have to look at the algebraic multiplicity when we're working with matrices in R, or will it only come up with matrices in complex numbers?
It will also come up with matrices in R, of course. Again, we'll talk more about that next week.
There are many people that want spoilers. So is there always a 0 row when you compute eigenspaces?
If you do it correctly. So the point is that that kernel needs to be non-trivial. So a kernel always contains a 0 vector, of course, but that's not a valid eigenvector. So if we get an eigenvector, then there needs to be a solution that is non-zero. That means the kernel is non-trivial. And that means the matrix cannot have full rank. And if it doesn't have full rank, it's a square matrix. So if you compute echelon form for a square matrix that doesn't have full rank, then that needs to end up with at least 1 0 row. So that's how you get that. If you happen to not get that, then you've made a mistake. Either your eigenvalue is wrong, that could be the case, or you've made a mistake in the reformulation somewhere, and you don't get the right eigenvector. And remember, the 0 vector is never an eigenvector. Don't write that.
Okay, so how do they know how many vectors are in the span? Again, spoiler.
Well, in that case, but by simply looking at the echelon form here. So basically, you see we have, in this case, 2 pivot elements. We have 3 columns. So that leaves us with the 1 free variable, and that's the number of vectors in the span. Yeah, basically that's how we solved linear equations in Math 1 already. You can also know that, of course, by looking at the multiplicities. But again, we'll talk about that more next week. Or confuse anyone who didn't watch the videos yet.
And then someone wants the exact definition of kernel.
The exact definition of kernel is, so we have a kernel of a matrix. Let's say the matrix is A. That consists of all vectors V in our, let's say this is an n by n matrix. And this V is also in Rn such that AV equals the 0 vector. So the set of solutions of the homogeneous linear system A times V is 0. That's the kernel.
Okay. And then there was a previous question. If someone didn't take Math 1 and they would need to brush up on a little bit of linear algebra, what could they do?
There's a bunch of great videos online that you could watch.
Yeah, so that's what I said. They should probably still be on your YouTube page, right?
Yeah, the videos are still on the YouTube page. If you want the lecture notes, those would be on the Moodle page only. So if you, I guess you can't add yourself to that page anymore. If you want to be added to the Moodle course page, just write me a quick email. Be sure to include your TUM email address so I can find your account there. And I'll add you to last semester's Moodle course, and you can access all the materials there.
And do you happen to remember which videos you talk about the necessary topics?
Not really.
I would be impressed if you did, but they come with the title that tells you what the video is about.
Yeah. Also for each week, as in this year, there's a quick logbook, usually a one-pager with a quick overview of the topics and the corresponding videos. So just search the logbooks for the topic you're interested in, and you should quickly be able to find the videos.
Okay, so now there's a couple more questions coming in. Do we have to check for linear independence, or are the eigenvectors just linearly independent?
Well, at this point, technically speaking, at this point, you would have to check that. But as we will learn this week, eigenvectors for different eigenvalues are always linearly independent. And for the eigenvectors for one eigenvalue, we make sure that this is the case when we write down the solution. So the way I compute the solutions, let me scroll back to that two-dimensional solution here, like here, for example, I always make sure that this is the basis of the solution space. So these are linearly independent. And then with the fact we learned this week about eigenvectors of different eigenvalues being linearly independent, the rest is automatic.
Last question. So could it happen that you end up with 4 eigenvectors for a 3-dimensional matrix?
You can't end up with 4 linearly independent eigenvectors. Of course, there are more eigenvectors. I mean, if you have an eigenvector and scale it by any amount, you get another eigenvector. Any combination of eigenvectors for the same eigenvalue is a new eigenvector. So you could end up with more eigenvectors than you wanted to. But that would mean you haven't found a basis for the eigenspaces then.
Yeah, there won't be more than max 3 that are linearly.
So if you end up with more, you need to reduce that to get a basis. You made a mistake before, or at least you did not compute that to the very end of having a basis.
So you have a little bit left in this exercise, right?
I don't actually think so.
Oh, you're completely done, so we can do revisit 1, 2.
Yeah, I think I'm done with 1, 2.
Okay. No, I'm sorry. So someone wants to repeat the last step from 1 to B, how you got the transformation matrix.
How I got the transformation matrix. Okay,
and
basically
the diagonal entries. So yeah.
Basically, what I want to do is, also I have this basis here of R3, and I want to transform my linear mapping given by A to this new basis B. So A is the matrix representation of linear mapping with respect to the canonical basis, and I want to transform this to that basis here. So what I need to do is I need to find the transformation matrix between the bases B and C. And usually the easiest to write down, if that is what is given, is the transformation from B to C, right? Because that simply consists of the basis vectors of B, which are given in C coordinates. So I just take these basis vectors, write it as columns of a matrix, and I have this transformation here. And then to get the matrix representation with respect to that new basis that I want is, I take this basis B, that is a representation with respect to the basis C. And then I need to transform that to B. So I have an input coming in on the right-hand side in B coordinates. I transform those to C coordinates. I process those by means of the matrix B. And then I transform those, sorry, those C coordinates, wrong one. I transform those back to B coordinates. Yeah, that gives me basically the same mapping, but now from B to B coordinates. And all I need to add is this transformation here is the inverse of that transformation. So that also is true for the matrix. Means I can, instead of B transformed C, I can also use the inverse of that here. Times B times, so that. And now either you compute that or you know the result. And what the result, of course, has to be is the matrix with the eigenvalues on its diagonal. Because if we're transforming into this new basis here, well, this here is the first basis vector. So the coordinates of this basis vector here with respect to the basis B itself are 1, 0, 0. Right? Take 1 times that first basis vector, 0 times the second, 0 times the third. So what happens if I multiply my new matrix, the one that I obtained by this transformation here? If I multiply that with this vector, well, I get the first column of my new matrix. What does the result have to be? Well, remember, this is an eigenvector for eigenvalue 0. So that means if I multiply the matrix B times 1, 1, 1, the result is going to be 0 times 1, 1, 1. Yeah, eigenvalue, eigenvector. So that's the 0 vector. So the first column of my transformed matrix needs to be the 0 vector. And then the same happens for all the others. Let me do that for the green one as well as an illustration. So if I'm taking that green vector here, B times that eigenvector, again, that is an eigenvector with eigenvalue 1 this time. So that result is 1, 0, 1 times 1, 0, 1. And also if I regard this with respect to the basis B, confusing naming, that's the second vector in my basis B. So the coordinates with respect to that basis are 0, 1, 0. And that means if I multiply this new matrix here with that vector, I will get the second column. And the result must be exactly that vector. Now also in B coordinates, so I will get this one here. And that must be the second column, right? So I get basically exactly the unit vector multiplied by the corresponding eigenvalue. That's why I get the eigenvalues on the diagonal. Okay, I hope that answers that question.
I think it does. So the rest I will just type out. So I think that's it for now.
Good. So let's have a look at 1.3 then. For a quick application of what we've discussed so far. Basically, what we do now is we take eigenvalues, eigenvectors, and differential equations together and use that as a tool for determining solutions of differential equation systems. So here we're looking for a solution of a differential equation system that looks like this. We have y prime, so y is the function we're looking for. And we have a matrix 8 minus 1 minus 2, 7 times y of t. And this y here is now a vector that consists of 2 functions to be precise, right? So if one y1 function and one y2 function. So when I write y, I always mean this vector consisting of 2 functions. And we also have an initial value here. Y of 0 is the vector 1 and 2. And the task is to determine the solution for this initial value problem here. Now, I already said what we do is we transform that to a differential equation system with a diagonal matrix, because that would yield 2 decoupled differential equations. And we have already seen how to solve those. So what we need to do first is we need to find out how to diagonalize that matrix A. So that's going to be the first step. Diagonalize A, if possible, of course. So in that case, we don't have the eigenvalues yet, so we need to compute those first. To compute the eigenvalues of A, what we do is we compute the so-called characteristic polynomial. That's called PA usually, of lambda, and that is the determinant of this matrix A minus lambda times identity matrix. We want to find out when this determinant is 0. So in other words, we want to find out when this matrix does not have full rank, when it's not invertible, because those will exactly be the lambda values where we get a non-trivial kernel. Yeah, so those are going to be the eigenvalues, the roots of this characteristic polynomial. So we need to compute that determinant. We have this matrix A, and we subtract lambda on the diagonal. So that yields, let's see, 8 minus lambda times 7 minus lambda minus 2, or lambda squared minus 8 lambda minus 7 lambda, that's minus 15 lambda, plus 7 times 8, that's 56 minus 2 is 54. So that should be the characteristic polynomial. And we want to find the roots. So we just use the quadratic formula for that. That is, let's see, minus 15, that is plus 15, plus minus the square root of 15 squared, minus 4 times 54, divided by 2. That is 15 plus minus 15 squared is 225, and 4 times 54 is 216. So we get the square root of 9, or 15 plus minus 3 over 2. And that is, well, 15 plus 3 is 18 over 2. That would be 9. And 15 minus 3 is 12 over 2. That would be 6. So we get lambda 1 equals 9. Lambda 2 equals 6. And those are the eigenvalues. At that point, we have 2 different eigenvalues. And after this week, you'll know that this also means we get 2 linearly independent eigenvectors. So we can be sure that this matrix can actually be diagonalized. But of course, to compute the solution, we actually need to do that. So we need the transformation. And that means we also compute the eigenvectors. So let's start with the eigenspace for the eigenvalue 9. It's the kernel of A minus 9 times I2. Or the kernel of, let's see, minus 1, minus 2, minus 1, minus 2. Yeah, so obviously those 2 rows are multiples of each other. So that's the same thing as the kernel of minus 1, and then 0, 0. And we solve that by saying, well, this is a pivot. X2 is free. So that means we set X2 to 1, for example. And then X1 has to be minus X2 or minus 1. So that's one possible eigenvector here. And we can make the same computations for the eigenvalue 6. So the kernel of A minus 6 times I2. Let's see, it's 8 minus 6 is 2, minus 2, minus 1, and 7 minus 6 is plus 1. So again, the second row is a multiple of the first one. And we get kernel of 2 minus 1 minus 2, 0, 0, like that. Right, and that is the span of, let's see, to compute x1, we have to divide by 2. So it's probably better to use 2 instead of 1 for x3. And then x1 is 1 over 2 times x3, so that's 1. Okay, that gives us the two eigenvectors. So those are linearly independent. We have a basis of R2 that consists of eigenvectors of A. So that matrix can be diagonalized. So that means we can write down a transformation matrix. Let's call that S minus 1, 1, 1, 2. And with that matrix, we get S to the minus 1 AS is the diagonal matrix with the corresponding eigenvalues on the diagonal. And those were 9 for the first eigenvector and 6 for the second eigenvector. So we know how to diagonalize that now. Now to apply that to the differential equation system, what we do is we apply a substitution. And that substitution is y equals s times c for a new function c. And with that transformation matrix S here, let me just compute it. Why do we do that? Well, basically the idea is the following. We have this differential equation y prime equals a times y. Now, if y equals s times c, then that means y prime equals s times c prime. S is a constant, so differentiation doesn't involve that. So y prime can be replaced by s times c prime, and y can be replaced by s times c. And now solving that for c prime yields s to the minus 1 as times c. So what we get here is exactly this expression here. And we know what that is because we've just computed it, right? That was the whole point of computing this s here. So what we get is a new differential equation system in now the functions c. That says, well, c prime is 9006 times c. And what that in turn means, if we write that out, we have c1 prime of t equals 9 c1 of t, and c2 prime of t equals 6 c2 of t. So what we did is we decoupled the system. And that means each row of the new system is a differential equation on its own, independent of the others. And we can solve those independent of the others. So simple solutions here. We get c1 of t equals e, well, constant, any constant, times e to the power of 9t. And c2 of t is a possibly different constant times e to the power of 6t. Now we have a solution for the new differential equation system C. And once we have that, we can just transform it back. So that's going to be step 3. Basically, now we undo the substitution. That was y equals s c. So our solution y is going to be s times the solution c of t that we have. Remember s was, where do we have s? Minus 1, 1, 1, 2. Minus 1, 1, 1, 2, like this. Times, and our vector c was, the c1 was c1 times e to the 9t, and c2 e to the 6t. So what do we get? Well, y of t is then minus c1 e to the 9t plus c2 e to the 6t, and c1 e to the 9t plus 2 c2 e to the 6t. So that's our general solution with constants c1, c2 in the real numbers. And finally, we have to determine those constants. That's step 4 then, by using the initial value conditions. So we determine c1, c2 through initial values. And those were, if I remember, yeah, better look it up, y of 0 equals 1 and 2. So what do we get here? Well, y of 0, if we substitute 0 into these solutions here, we get minus c1 plus c2. Remember, e to the 0 is 1. And we get c1 plus 2c2. And that is supposed to be 1, 2. So what we need to do is we need to solve this equation system for the constants c1 and c2. So we solve, let's see, minus c1 plus 1c2, c1 and 2c2, and the right-hand side is 1, 2. So let's add the first row to the second one, minus 1, 1, 1, and here we get the 0, 3, and 3. And that means we get a unique solution. So C2 is then 3 divided by 3. That's 1. And C1 is minus 1 plus C2. So that's minus 1 plus 1, that's 0. And that means our solution is y of t. If we look back on that one here and then substitute those values for the c. So this is 0. That means that part vanishes here. And c1 is 1. So we are left with e to the 6t and 2 e to the 6t. E to the 6t, and we have 1 and 2. Right, and that should be the solution that we get here. So, finished. Questions?
So far, not really to this one. There's one about the video going on YouTube after, because the streaming normally gets deleted. And I thought it would be on YouTube. It will, right?
Yeah. So YouTube normally saves the stream. So it's currently being streamed to YouTube. That stream should be available for a while. I usually delete that when I start uploading the final video. So I make some minor editing for that final video, and then I delete the stream when the final video is up.
But some version of the central exercise should be on YouTube.
Yes, correct.
Yep.
Either watch live stream, the recording of the live stream, or sometime tonight I will upload the final video.
And then I have nothing else. So
that's it.
Seems like it. Yeah.
Okay, wonderful. So as I said, we have one more week to discuss these questions on eigenvalues, eigenvectors. I know that's a lot to process for 2 weeks. So don't feel bad if you don't get it on the first try. bring your questions next week, or of course, with the tutorials. And after that, we'll start with a somewhat different topic. We'll talk about multi-dimensional calculus then. So I hope I'll see you next Monday, or of course, on Thursday in the tutorial class then. Thanks a lot to Aline for moderating. Goodbye.